Hello everyone, today I would like to show you something about orthotropic materials in Karamba3D. For this example, I set up a simple cone geometry using this surface component. I meshed it using the Karamba3D mesh B-Reps component. Then turned the mesh into shell elements, assembled the model and calculated it. In order to get some displacement results, I have to add here a load, which in this case is a constant mesh load. For the mesh where I apply the load, I use the mesh of the structure, and the load is a load in global z direction and has a value of 1 kilonewton per square meter pointing downwards. For a shell, it's quite essential how the shell is supported. I would like to show you how the ideal support of such a shell looks like. Ideal means that the supports are oriented in such a way that only in plane support reactions result, because otherwise, in case of transverse support reactions, we would get bending moments in the vicinity of the boundary. So for this, I first of all selected all the nodes which are at the base of my structure. For this, I use here all the points which are part of the mesh, and via this selection component, which was done by Georg Lobe, I can now select only those points which correspond to a specific condition. In this case, their z coordinate needs to be between -1 e minus 5 and +1 e minus 5. And now comes the orientation of the supports. For this, I used cone geometry from above here. I take the points, map them onto the surface. This gives me the UV coordinates, and from this, using the evaluate surface component, I can get in each point now a coordinate frame, which I use here now to orientate the supports. And this looks then like this. So you can see here that the supports are only in tangent and radial direction. And together with the loads, I get here now a nice uniform displacement pattern, as you can see here. So this would be the undisplaced situation. And here this is the displaced situation. So you can see the shell is able to breathe, so to say, and no bending moments occur here at the boundary. In order to specify an orthotropic material behavior, one needs to control also the orientation of the shell elements. By default, the orientation of shell elements is such that the local y-axis is parallel to the global y-axis. In order to see the local axis, we can enable their display here at the model view component. in each mesh face, I decrease now the mesh density. So in each mesh face, which is also a final element, I get here this tripod where the red, green and blue lines correspond to the local X, Y and Z axis. And if one looks from above, and maybe let's disable here the preview of the displacements. So as you can see, the local y-axis here, the green lines are parallel to the global y-axis. In case that this is what you want, one doesn't need to do anything else. The orthotropic material properties can be set here via this material properties component. The directions 1 and 2 correspond to the local X and Y direction. We can specify here two values for the Young's modulus. G12 is the in-plane shear stiffness. The correct new value is for orthotropic materials quite complicated to retrieve. Therefore, if this value is set to -1, a plausible assumption is used based on a paper by Huber, where the details can be seen here in the help text. G31 and G32 are the transverse shear stiffnesses in direction 1 and 2. Gamma is the specific weight, alpha, T, the coefficients of thermal expansion in the 1 and 2 direction, and here we have the tensile and compressive strength values. T12 is a shear strength and F12 is the Tsai-Wu coefficient, which only takes effect in case that the Tsai-Wu strength hypothesis is chosen for the material. By the way, if you right click on the icon, you can expand here the value list, and this makes it then easier to select the different possibilities regarding the strength hypothesis. Now let's see what happens if I change here, for example, the Young's modulus value in one direction. Remember, this is the direction which is approximately parallel to the X direction. I will refine the mesh now again and disable the preview of the local axis. Okay. So this leads to a non-symmetric deformation. You see the material is now weak in the in this direction, which means that bending moments in this in these areas here lead to these dents. If we change now the other directions, the same occurs now the other way around. If you want to have a structural behavior which is symmetric, we need to orientate the local element coordinate systems in such a way that they are symmetric with respect to the middle axis of the cone. This can be done like here. I will now make the mesh now a little bit rougher so that it's easier to see what happens here. I use here the original surface, the mesh which comes out of the mesher. This component here gives me the middle points of each mesh face, which get mapped onto the surface, and again via the UV coordinates I can retrieve here the coordinate system on the surface in arbitrary points. For example, here in U direction. So you see now that the U directions are all tangential to the surface, and using this orientate element component, I can now specify the local coordinate system of each shell element. And if I do this now, one can see that the deformation is now quite differently. I again make the mesh here denser. And now if we, for example, change here the Young's modulus in the wrong direction, we get now a symmetric deformation pattern. As you can see here. So that's it. Thank you for your attention. Goodbye.